Hi everyone, welcome to the Nuvoton Level 1 training. I'm Abby, Field Application Engineer of Nuvoton. Today, I'm going to introduce the I2C function of our NuMicro M031 and M032 series. Here is the agenda. We'll talk about what I2C is, what application I2C could be used, and the protocol and feature of I2C. We will also talk about the block diagram and registers. What is I2C? I2C is integrated circuit. It is a type of serial computer bus. I2C is a way of allowing multiple electronic devices to communicate with each other over a single pair of wires. The pair of wires are bidirectional bus. One is called SDA, serial data line. The other is called SCL, serial clock line. By the name of the wires, you could get the idea that SDA is used for data transfer and SCL is used for clock synchronization. For the circuit part, since both SDA and SCL are open drain pins, they both need a pool of resistor connecting to VDD. The application of I2C is usually for low-speed data transmission. The devices I2C could control are addressed devices. For example, EPROM, gyro sensor, temperature sensor, or audio codec. Let's talk about the protocol of I2C. In a standard I2C communication, there are 4 stages. The first stage is a start signal. After start signal, the slave address and whether the operation is read or write is sent. This is the second stage. Then, in the third stage, do the data transfer, and then use a stop signal to end the communication. However, instead of sending a stop signal, it could also use a repeated start signal to continue with another communication. All the data transmission starts with the most significant bit and ends with the last significant bit. Besides, when SCL is high, data line should keep stable. The data is valid when SCL is high. When SCL is low, it is allowed to change status of data line. When the bus is free, the master can initiate a transfer by sending a start signal. The start signal is SCL keeps high, and SDA goes from high to low. The master can terminate a communication by generating a stop signal. The stop signal is SCL keeps high, and SDA goes from low to high. Besides, if the master would like to continue a next transmission without releasing the bus, it would use a repeated start signal to make it. The repeated start signal is the same as the start signal, which the SCL keeps high and SDA goes from high to low. The data transmission of I2C is 1 byte each time. After transferring 1 byte data, an acknowledge would notify if the transfer is OK. Therefore, each transferred byte is followed by an ACK or a non-ACK at the 9th clock. If the acknowledge is in low level, it means an ACK. The transmission is OK. If the acknowledge is in high level, it means a non-ACK. Non-ACK has 2 kinds of meanings.
One is used to indicate that there is something wrong during the transmission. The other is used especially in the master-receiver mode. When the master is done reading data, it uses a non-ACK to indicate the slave that the read operation is done.
We have talked about that there are 4 stages in an I2C communication. Let's take a closer look at it. We show how master writes data to a slave and reads data from a slave. Blue color means the transfer direction is from master to slave. Gray color means the transfer direction is from slave to master. For writing data to a slave, the master starts with the S, which is the start signal, then identifies the slave address and the rewrite bit as 0, which means write operation. The target slave then sends an ACK to tell the master to continue. Following are the data transfer from the master to slave for write. Each data chunk transfer will follow by an ACK or a non-ACK. After all the data are transferred, the master terminates the communication with a P, which is the stop signal. For reading data from a slave, the operation is similar. It starts with a start signal, then sends the slave address and the rewrite bit as 1, which means read operation. After the slave sends ACK to the master, the slave starts to send data chunks to the master because it is read operation. The same, the master will respond with an acknowledge to notify the slave. Finally, a stop signal is used to terminate the communication. Here's the bus signal of I2C write data and I2C read data. You can match the 4 stages with the waveform. Notice that I2C samples the data from SDA when SCL is going from low to high. In I2C read data part, you can see the data bit value sampled by each clock.
In this example, we will show you how to combine write operation and read operation together for accessing EPROM data. Since EPROM is a 16-bit address ROM device, to access EPROM space, the master has to write a 16-bit address first to tell EPROM which space it wants to read data from. After that, the master reads data from the address of EPROM. It means, for the master, it has to send write operation to EPROM first. The write operation will give the high byte and the low byte of the address to the slave. The master sends read operation afterwards and waits for EPROM to respond the data. Each I2C communication is either write operation or read operation. They cannot be mixed together. However, we don't want the write operation and the read operation to be separated. Therefore, a repeated start signal, ST, is used between the write operation and the read operation. Instead of sending a stop signal after the write operation, the master sends a repeated start signal to continue using the bus. This mechanism makes sure that the process of reading EPROM data won't be interrupted. Let's see the graph below. To read data from EPROM, the master initiates the transmission with STA, the start signal, then sends the address of the slave and specifies the rewrite bit as W, which means write operation. Following 2 bytes are the EPROM address that we want to read data from. You can see the master receives ACK from the EPROM, so the master can keep sending message. The master initiates a transmission with ST, the repeated start signal, to continue using the bus. The same, the master sends the address of the slave and specifies the rewrite bit as R, which means read operation. EPROM responds an ACK and then sends the data. Notice that in this graph, the last acknowledged is a non-ACK. It means the master has been done the reading and wants to end the communication. At last, the master terminates the transmission with STO, the stop signal.
For EEPROM accessing, we have provided API to make it. This API, I2C write MultiBytes to registers, is used to write data to EPROM. You can specify slave address, data address, and data to be written by this API. This API will automatically handle all the operations to write data to EPROM. Besides writing, we also have an API for reading data from EPROM. This API, I2C read MultiBytes to register, is used to read data from EPROM. The same as the writing API, you can specify slave address, data address, and data bytes to be read by this API. This API will automatically handle all the operations to read data from EPROM. Now you know how I2C works. We would like to show you what I2C features we provide for M031 and M032 series. First, I2C supports two-speed mode, standard mode, which is 100 kbit per second, and fast mode, which is 400 kbit per second. However, if you use M480 series, I2C would support one more speed mode, which is fast mode plus, and the speed is 1 megabit per second. I2C supports both master and slave mode. It also supports multiple address recognition. Besides, the I2C function supports waking up CPU from power down mode. Also, we integrated with PDMA to provide faster data access capability. For the addressing, we support 7-bit addressing mode, which means it could control up to 128 devices. We provide a timer to avoid the bus being occupied for a long time. A 14-bit counter is used to count. When time is up, the bus will be released. The setup hold time is programmable for I2C function. All the operation modes our I2C function supports are listed below. There are master transmitter, master receiver, slave transmitter, slave receiver, and general call. I2C will work in different modes by its role and data transmit direction. From block diagram, you can see that the clock source of I2C is from APB interface, which is PCLK. The control register and clock are used for the I2C bus protocol control. There is also a wake-up control that allows I2C to wake up CPU from power down mode. The PDMA here is for faster signal processing. The control register of I2C is used to tell the status of I2C. The INT-EN bit is used to define if I2C interrupt is enabled. The I2C-EN bit is used to disable or enable I2C function. The STA bit corresponds to the start and repeated start condition. When STA is equal to 1, it is going to transmit a start or a repeated start signal when bus is free. The STO bit corresponds to the stop condition. When STO is equal to 1, it is going to transmit a stop signal. The SI bit will be set to 1 when status is changed. For example, when the value of status register changes from hex value 8 to 18, Si will be set to 1. The AA bit is related to the ACK. If AA is equal to 1, an ACK will be sent at the ninth clock. If AA is equal to 0, no ACK will be sent at the ninth clock, which means non-ACK will be presented on the ninth clock. There is a status register in I2C. It is used to show the state of I2C. The value of status register will change stage by stage during the I2C processing. For example, when a start signal is sent, the status register will be changed to hex value 08. When the slave returns ACK after the master sending slave address and rewrite bit, the status register will be changed to hex value 18. And if the non-ACK is returned, the status register will be hex value 20. Therefore, by the value of status register, I2C controller would know what state it is now and what to do afterwards. Let's use the EPROM example again to show you the mapping between I2C processing flow and the status code. EPROM is a 16-bit addressed ROM device. The address of it is 16 bits. In order to read data from EPROM, the master has to identify the address of the target data. As we mentioned before, the master has to trigger a write operation and then a read operation for reading EPROM data. For the write operation, the master starts with sending a start signal. The status register then is changed to hex value 08. After getting an ACK from sending the slave address and the write bit, the status register is changed to hex value 18. Then, the master has to send two data chunks to identify EPROM address. After getting an ACK from sending each data chunk, the status register is changed to hex value 28. However, if non-ACK is received, the status register will be either hex value 20 or 30, depending on the flow. If a stop signal is sent, the status register will be hex value F8. This is one of the flow that we got from our technical reference manual document. The flow is a master transmitter flow. It is similar with what we have shown you before. The point is that the value of status register will be changed by the behavior it is done or by the acknowledge it receives. The I2C controller can also decide what to do according to the status register. This is part of the EPROM data accessing code. From the source code, you can see more clearly that it will trigger different actions according to different status code. In Nuvoton BSP, we provide APIs for I2C function. For example, you can get the status code by calling I2C getStatus API. You can write data to I2C data register by calling I2C setData API. You can easily make what you want by calling I2C API we provide. Besides API, we also have I2C sample code for your reference. There are EPROM accessing sample code, master mode sample code, I2C with PDMA sample code, etc. You may check our sample codes for more detailed information. Above is the introduction of I2C. Thanks for watching. You could subscribe our channel for more information. Besides, please do not hesitate to contact us if you have any question.